Stars are objects in our cosmos that very far away. I mean, we have the sun that's somewhat close to us, but it's still kind of far away. And based on what we learn in scales of our solar system is a quarter light years in size. And when we talk about stars, we define their separation as light years. So just think about our solar system being a quarter of light year, and the separation between stars being something as 10 light years in average. I mean, the closest star to us, Proxima Centauri, is about 4.3 light years. And it's if you take the sun and you shrink down to the size of a pinhead, so Proxima would be about 15 miles away in another pinhead. So just give us some sense of how separated, how diluted, how spread out our universe is. And then comes to the question, since we are studying a science course, come to the question, how do we know about stars? I mean, have you ever gone and visit all the stars that we talk about, of different sizes and surface temperatures and evolutionary stages? Have we visited them all, and collect samples and learn about them? I mean, exactly how do we know about them? Since as we advanced in our 17th century, we learn that um, science, as we know today, is something that's not enough to come up with nice, elegant statements. You have to be able to prove those statements, and you should be able to um, offer a worldview or a theory or a statement or a hypothesis that is able to be negated. Let's not forget that scientific statements are not absolute truth, are the best statements we have to explain certain events. And if in the future more information and more data is made available, then we might improve and modify our explanation, our theory. And that's what science is all about, is an ongoing process of better describing how nature and how the landscape we are in change as we move forward in time. So then, going back to astronomy, how do we know about stars? How can we measure stellar properties? So the technique we use to measure stellar property is considered scientific, although we are not collecting samples of stars and bring to the laboratory. So it is scientific because it's based on methods that have been tested in the laboratory. And which methods are those? Well, you could summarize the main points, the main tools astronomers use to describe the universe. You could separate them or characterize them in two major uh, groups. And the first group is what I could call all that information that can be derived using spectroscopy. Spectroscopy, let me write this down. By the way, this is my first question that you have to put in your discussion. So there are two basic techniques astronomers use to investigate the universe. And what are their names? That's the first question in the discussion that is now opening. So the first one is spectroscopy. Is spectroscopy. Copy. And as the name says, it uses spectrum. The second technique is called photometry. Photometry. Oops, I think I did it wrong here. Photometry. And photometry is based on a technology that counts the number of photons that arrive in a given detector. And so, for instance, if the star becomes bright, the number of photons increase. If the star dims, the number of photons diminish in that particular color band we are observing. So spectroscopy is based on spectroscopic analysis of a spectrum. And a spectrum, if I can move forward, I can show you, this is a spectrum right here. It has these traces, and these traces are lines. In this case, they are emission lines. Emission lines. Why they are called emissions? Because the color and the traces appear on top of a black background, and then you can see them as an emission right here. As opposed to absorption lines, they appear when, in this case, so you have a continuum, which is described right here. So there is a continuum, and the transition, the lines are below, in flux, below the continuum level, and they are called absorption lines. And then you can see, as opposed to emission, the absorption lines are darkened. I mean, it's less light, it's less emission than it's shown in the continuum. The continuum appears in here as a rainbow. So, and the main point is white light, or the light the sun emits, or the light that comes out of a filament tube. So that light is a combination of light of all possible color bands. And when this emission, when this light moves and passes through a region that has a cold gas, the elements in the cold gas, the molecules, the atoms, selectively absorb photons of a very specific color or very specific frequency, and by doing so creates these gaps, creates these dark lines. So when you see these dark lines, in fact what is happening is the absorption, the retrieval from the spectral distribution from the rainbow, the retrieval of those particular photons in this particular wavelength. Why? Well, when the atoms absorb these photons, the atoms become excited, and then the electron is moved up to a more energetic orbit. And eventually, this atom can then use that excess of energy to distribute that throughout the gas by collision, or can emit a radiation in a different orientation, and so the observer does not see that photon anymore. So it's kind of a loss, and that's why you see a depletion in the spectrum. So again, those are the two techniques that astronomers use, or the two tools that astronomers use to measure stellar properties. And again, this is one of the first question I have in my upcoming discussion number 4. What are the tools of astronomers? And then you have to say, okay, spectroscopy and photometry, and you have to explain what they are, not just say what it is. You have to explain with your own words, and please do not copy and paste from internet this, because this is not nice. Okay, so now how can we use these techniques to find things? And let's start with spectroscopy, since we have a spectrum here. Have you heard of Doppler effect? And I think I put some links in our course for Doppler effect. You have also some extra credits on Doppler effect. So Doppler effect is also a technique that allows the highway patrol officer to give us tickets if we speed up above a certain limit. So what is done is he has a little radar or a lidar that emits some sort of radiation, and I think that the radiation that is now being sent is infrared. It used to be radio, but now it's infrared, I think. And and that radiation, that light, travels towards the car and then bounces off towards the officer, who has a receiver in the same instrument that capture the signal they're arriving. Now, there is something interesting, and that is that there is a difference between the frequency that the officer sent and the frequency the officer received. And when you do your calculations, when you learn physics and you do a little calculations, you realize that the difference in frequency, or if you translate that in sound, the difference in sound's pitch is due to this phenomenon we call Doppler effect. And then you can use your equations to pin down the velocity in which the car was moving towards you or away from you. So, and it so happened that if the car moves towards you, the frequency you detect is a frequency higher than the frequency sent. So, in terms of sound, the pitch is a little bit higher. And if the car is moving away, you also can measure the speed, but the frequency received is lower. So the sound is a little bit of a lower pitch. Okay. So Doppler effect is a fascinating and a versatile tool that we use to determine if, for instance, a star rotates and at what rate the star rotates. Or in terms of the sun, we can use Doppler effect to move the speed in which cells are moving towards us, and the edges of the cell, as we studied in the previous chapter, the supergranulation or the solar granulation, are cells of gas bubbling up and down. So it goes up in the center of the cell and then falls down the edge. So if you take the telescope and you point exactly to the center of one cell, you detect frequencies or colors or transitions that are slightly moving towards higher frequency. But if you point your telescope exactly to the edges of these cells, you detect a frequency that's slightly less. And you can measure that, and then you can pin down the circulation, the speed in which the cell circulates in the solar interior. Doppler effect can also be used in binary system when you have two stars, one circulating the other in the so-called center of mass. So let me show you. I think I have a I have some animation here showing that. The observer, I think, is somewhere here. I'm not sure. But you have observer somewhere. And this is a star system that consists of a bigger star, hotter, and a cooler star, which is redder. See, the color also tells us something about their surface temperature. And spectroscopic binary is a group of two stars that we might not necessarily resolve them using telescopes. In fact, images of telescope. What I mean is, let's say you go to the observatory and then you look through the eyepiece, and then as you are looking through the eyepiece, you devise a group of stars much close to one another, and then you learn they are a binary system. So these binary systems are visual binary. So you can see those two stars independently. Now there is another group of stars called spectroscopic binary. So you don't see them separated or detached. So when you look at a spectroscopic binary star, so your telescope is not being able to resolve them independently. You see just one star. And in fact, this one star you see is a combination of two of them, but it's unresolved. But if you use spectroscopy, you can separate those two stars and get information about those two stars. So let me show this. So you observe the system that now is not moving, and then you detect two specific transition lines, right? So you have one and you have another. So let's run the show. See what happening? So you have two lines, two specific transitions. Line one is more in the violet or almost near the green part of the spectra. And you have another one that is more towards the red part of the spectra. And I'm redoing this on and on and on. So let me stop here. So in this configuration, you have the two stars in such a way that the red star is moving to the left, and the blue star, let me see what it was. Yeah, so the red star is moving to the left and the blue star is moving to the right. So if this green point is the observer, I think it is. If this green point is the observer, so you see the trace line of this red star moving towards a higher frequency, more towards the blue. Blue is higher frequency. And whereas the trace line of this second star, the one that is closer to the center of mass, seems to be moving more towards the red. So you have a blue shift transition being detected here and a red shift transition detected for this other star. And once this red star reaches this level down here, the lowest part in the curve, you're going to see its trace transition being blue shift. So take a look there. See that? Blue shift, red shift. Blue shift now and red shift. See that? Now observe the same thing with the big star. When the big star approaches the observing point, its trace goes blue shift, and when it goes away, it red shifts. Okay? Let's see, I think there was another one here. There you go. This is a good one too. So we have the two stars, and then you can see the frequency of each one of them. You see the wavelength. The wavelength, this is the wavelength, right? The wavelength is not the same. So the wavelength is the one indicative of this particular transition. But when the star that emits that wavelength goes away from the observer, from the spectrometer, it goes blue shifted. It goes to a lower frequency, whereas when it comes towards, it migrates to a higher frequency. See it again. See how the wavelength changes. And I hope this became clear in the extra credit. There was an extra credit Doppler effect that helped that a lot. So spectroscopy, one of the applications of spectroscopy is Doppler effect. Now, where Doppler effect is used, not only for stars, but also for galaxies. So we can observe galaxies that are billions of light years away and use powerful telescope because they are very dim systems. And then can use power telescope to create these rainbows and find out which transitions you can observe. And by analyzing those transitions, you can estimate percentage of stars in these galaxies as far as their surface temperature and evolutionary stage is concerned. You can point the telescope to nebulae, and by doing so, figure out what is their chemical composition, their temperature, and and density. You can do all of that. So that's so much for spectroscopy, and photometry is a technique that counts photons. So when you take a picture, when you see these beautiful Hubble pictures of various celestial objects, what you're really using is an adaptation, if you will, of photometric techniques. You are collecting photons of light on a certain amount of time, and then you are using the information collected to highlight features on that particular picture. Let me so. Now let me talk about magnitude. Photometry allows, as I mentioned, allows astronomers to measure the amount of radiation, the amount of light that arrives on a telescope, and you can use this technique to measure brightness, the brightness of a star, the brightness of a system. So there is something called, and depending on which book you read, it comes with slightly different terminology, and that is intrinsic brightness. So intrinsic brightness is the total energy, the intrinsic energy the star itself sends out to space. And brightness alone is the brightness you here on Earth detect of that particular source. So, but I prefer to use the term luminosity to describe here, luminosity, to describe the total energy that the star or the galaxy or the quasar is sending on a time scale. Okay? Now, how does luminosity, which is the intrinsic brightness of star, which is the energy the star itself sends out in space, how does luminosity relate to brightness, which is the amount of energy you receive here? So if we call brightness the letter B, brightness, which is the energy we receive here, is equal to the luminosity, the energy the star sends out, divided by some number, 4 pi r square, and 4 pi, and I'm not going to write this, but you have 4, in fact, I should write 4 pi, divided by the distance to the star squared, to the second power. Now, and then you're asking me, how in the world you get this equation? Well, this equation is in fact derived in a laboratory. If you take the Astro-10, this could be one of the lab exercise you're going to perform in the lab. So light and radiation has this property of diluting itself in such a way that if you move a specific distance ratio from the source, the intensity of that radiation falls with the square of that distance. So if you double the distance, now the intensity you detect falls by a factor of 2, the double, time itself, 2 squared, 4. If you triple the distance, the intensity you detect falls 3 to the square, 9, 16, and 25, and so on, and so on, and so on. That is the so-called inverse square law. Inverse square law. So the magnitude, the brightness you detect on celestial objects gets dimmer as you move away from the source. And this is the basic equation governing this fact. Okay, that's the inverse square law. how important how important this inverse square law is for us, for astronomers? Well, it's very important. So let's say that you observe an object out there in the space. Let's say a star that for all purposes is identical to the sun, or a H2 regions. I don't know if you have come across an H2 regions, which is a region that is of diluted gas and has hydrogen Balmer alpha in emission and has this pinkish coloration. That's an H2 region, ionized hydrogen region. So if you observe an H2 region, you can you know quite well based on its spread what should be the luminosity of it. So there are certain objects out there, and we call them astronomical candles, like the candle you light up in Christmas or in holidays. Um, Astronomical candles are objects you know because you observe them carefully close by. You know how much energy they send out. So if you know the energy they are producing out there, you can observe them and use the inverse square law to find distance. Why? Well, because you know their luminosity, because you know them. Like you know the luminosity of an H2 region, the luminosity of a main sequence star, you know all of that. And then you observe the brightness using telescopes, right? You know how bright they are. You can measure how many photons you collect from those sources. And by applying this equation, look how powerful that is. You can find the distance to the stars. So you don't actually need a ruler out there to specify distances to quasars, to galaxies, so none of this. If you know the luminosity of it, then you can observe it, and then you get a very robust determination of distance to these sources. One fine example that we studied in the sections of stellar evolution is um, of supernovae. So supernovae are stars that explodes, and in particular, a supernova type 1 is a binary system consisting of a white dwarf with a companion that is dumping material on it. So when the white dwarf goes above the mass of 1.4 solar mass, because of Chandrasekhar limit, the star can't hold on anymore and explodes, and we call that supernova type 1 explosion. Now, what is the beauty of it? Well, because we know that 1.4 times c squared, 1.4 solar mass, which is m, times c squared, the speed of light squared, is equal to a certain amount of energy. That's Einstein equation, right? E is equal mc squared. And then we know the energy the star sent out. And then we can observe that star exploding if you find it in proper time. And then you can use that to establish distances. And that's how astronomers, the technique astronomers use to find out even that the universe is not only expanding but accelerating. Okay. So magnitude is a scale that is based on the brightness, and it has a logarithmic scale associated to it. So again, stellar properties are based on. You don't need to go to the object or to a star to find its properties, but you need to observe and have powerful telescopes to observe that. And I think those are the questions I wanted you to describe. First, the tools of astronomers, you know which one they are, and explain what they do, and in particular give some descriptions of Doppler effect, how important Doppler effect is to come up with information about objects. So in particular, we are going to study um, Big Bang and the expansion of the universe next week. And Doppler effect is fundamental. That's how we know space is expanding. We know space expanding because above certain distance of 100 million light years, we see all galaxies flying away or moving away from us, no matter in which direction we look. And that is because of Doppler effect. So Doppler effects allow us to measure that. Okay? So that's all. That's all for now. Thank you.